Problem on page 22 right here. It says 150 grams of NaCl completely dissolved. And now look at this. They give you this hint on this question that probably that hint will not be there on the actual test. They say it produces Na plus and Cl negative ions. If you recall, all of these colligative properties are based on the number of particles that are floating in the solvent, right? The way the vapor pressure is actually compared is you take the X of the solvent, which is the mole fraction of the solvent, and you multiply it by the normal or what we call the standard vapor pressure of that. So basically, if you take a look here, we need to change 1 kilogram to moles. Well, 1 kilogram is 1,000 grams. We change that to moles by dividing it by 18.02. Since the mole fraction of the solvent is the moles of solvent over the moles of the whole thing, we have the 55.49 here, and we have the 55.49 here. If we take a look here, this is the moles of the NaCl. We have 150 grams of NaCl. Every 58.44 grams of NaCl is 1 mole. So that is the molar amount of NaCl. We multiply that by the Van Hoff factor of 2, because for every 1 NaCl, there are 1 Na plus and 1 Cl minus. So that means if we have 2.567 moles of NaCl, we have 2 times that 2.567 moles of particles. So that right there is what people forget. Then you add them together, and then basically you take 55.49 divided by 60.624. And what that gives you is a fraction. You know this type of fraction because this is a percent fraction. If we were to times this by 100, it would be 91.53% water. We don't change it to percent because we want to find the fraction of this 23.8 torr that is the new vapor pressure. Since these particles are here, that's going to cause attractive forces, and it's going to pull in the Na and the Cl and the water molecules. It's going to pull them in. So it doesn't require as much pressure on the surface of them to make them vaporize. So it's a fraction. What is the fraction? It's 0.9153 of 23.8, which equals 21.84. So then we multiply that fraction by the standard, or what it normally would be at that temperature for the vapor pressure. That's it. If you want to take a look, I rewrote the formula for the mole fraction of the solvent. X of the solvent equals moles of solvent over moles of solute times I plus moles of solvent. What? Others? Questions?
I had a quick question on number 10, I think on page 16.
Number 10 on page 16.
Yep.
Numeral 10 on page 16. The freezing point for tert butanol is 25.50. So there's the freezing point. And the K of F for tert butyl is 9.1. So there's my K of F. Usually tert butyl absorbs water on exposure to air. But the freezing point of a 10-gram sample of tert butyl is measured to be 24.59 degrees Celsius. How many grams of water are present in the sample? So we actually know that the change in temperature freezing is equal to the Kf. Tert butyl is an index of 1, tert butanol, times the molality. All right, then. So then we should be able to get the T of F. T of F is equal to 25.50 minus 24.59.
The answer is 0.91.
1. That's the T of F. And how many grams of water are in the sample? So we have that equal to Kf, which is 9.1 degrees per mole. 0.91 divided by 9.1.
The answer is 0.1.
Times the molality. So then it makes molality equal 0.1. And that is moles of tert-butyl, moles of water divided by the 10 grams, which would be 0.0100 kilograms of the tert-butyl. So,
Well, wait, Mr. Jackson.
yes.
Why would you put the moles of like the grams of the T-butyl at the bottom? Isn't it the solute?
This would be, actually, it's the molality is 0.1 moles per kilogram of tert-butyl. That's the question here. How do I know that the tert-butyl is a solvent for this? Because we're dealing with what freezing point?
Oh, you're dealing with the freezing point of T-butyl, like the original like T-butyl, not water.
You got it.
Oh, if it started with 0, then you'd have to take water into consideration as a solvent.
I'm sorry.
If it was like the original was like 0, then water would be the solvent.
Yes.
Okay, that makes more sense. Thank you.
Sick. Let's see if I can do this now. They want how many grams of water in the sample? So we have 10.0 grams of this sample. Every 1,000 grams is 1 kilogram. And since it's a 0.1 molal solution, every 1 kilogram has 0.1 moles of H2O. And every 1 mole of H2O is 18.02 grams. 10 divided by 1,000 times 0.1 times 18.02.
The answer is 0.01802.
0.018, 3 significant digits. Nope, 2 significant digits based off of the subtraction here. So there we go. Yeah. That problem is weird because you're not dealing with water as a solvent, right? If you would have figured that out, you'd have had an easy time with that. Yeah.
Oh, Mr. Jackson.
1 second.
Oh, sorry, I had here.
Hmm?
I don't understand.
What do you mean?
I lost.
Which part?
I don't understand.
0.91 is the change in temperature. So that's 25.50 minus 24.59. And that change is positive. We subtract it. That's why it went down. No what? No, actually, that's the K of F is this. It just so happens that they are close together. It just so happens that they're similar numbers. Basically, then we found the molality, which was M. And then I used the 10 grams of the sample to go from grams to kilograms, and then used the molality, 0.1 mole of H2O per 1 kilogram. And then I changed the moles to grams, and then I got my answer of grams. Equals 9.1 times the molality. Yep, here's the formula, K of F times M, right? This is the change in freezing temperature. That's the K of F, and that's the M. That's what we wanted to solve for. Like the actual number? Yep. So if you have A times B equals C, right? Then you would, if you wanted to find A, you would divide both sides by B, and that would give you A. That's what I did. I took 0.91 divided by 9.1 to get M, which is what I wanted, and that's the malleolity. I just didn't show it. I can do that. Divide both sides by 9.1. I would. Yep. Like that. 10 grams, 1,000 grams, 1 kilogram. 1 kilogram is 0.1 moles. That's the malleolity. Every 1 mole is 18.02 grams. That's from the periodic table for the molar mass of dihydrogen monoxide. Somehow we caught up to and are passing the other extra teachers. Aren't we usually the ones behind? Oh, you don't talk to their shit. He's not testing tomorrow. Oh, did he do shorter quizzes? Yeah, one of them asked him for the for Beers Law. For that, he got mad. Mr. Woods got mad because somebody asked, "Why exactly are we doing this? This seems random." I don't know who that was because that 10th period used to be my students, but I have long forgotten who they are. Right, unfortunately. Oh, yeah. Then you had Mr. Woods and you didn't have me. Oh. Did he get angry at you guys often? Okay, good. That he just said that I just I don't even know. Like, I mean, I don't know if angry is the right word or not, but it was funny. Quit wasting my distilled water. Quit wasting my soap. Are we good on that? The whole reason for us doing this was so that you guys could postpone and have this extra day. Have you not put in the work for the review on this yet? You guys, are you guys the guys that study for the test right before it, or yes? You are procrastinators. I always tell myself that I'm going to help out future me. No. I'm going to be so happy I got this done later. You need the pressure. Anybody at home have a page number and a problem they want to see?
Oh, I have a question, but I don't, it's not exactly about a page number. So will the change in like the freezing point temperature always be positive in our equation?
Yes. Those delta T's, that change will always be positive because if it's a freezing one, you subtract it from whatever the freezing point is. That's freezing point depression. And then if you need to, if it's boiling, then you add it to whatever it is. Boiling point
And then
elevation.
also, when we did mole fraction with like the solutions before, we didn't take into consideration like the Van Hoff factor. Why is that?
Because we didn't have what do you call it? We didn't have a colligative property going on. We were just finding the mole fraction.
So if there's no colligative property going on, we just find the normal mole fraction without the particles into
You
consideration.
got it. And unless it is to solve for a colligative property, like, yeah.
Okay, thank you.
Yep. I'm trying to think. It may have also been because we weren't dealing with we were finding the mole fraction of the compound instead of the solvent, of the ionic compound instead of the solvent.
Yeah, I think so.
That could be it also. Yeah, it'll be very clear whether or not you need to do that Van Hoff factor in there or not. Another thing is, I mean, what if it is not a ionic compound? What if it's a molecular compound? Then what is the Hoff factor for that?
1.
1, right? So that also could have been why we did not see that come into play. Yeah. 4 on 15. Uh, 4 on 15. Looks like we already did this. So let me get a scrap paper and we'll do it again. You know what else is amazing? Yeah. You got it. But CP Chem has finally caught up with you guys. They have just started malaria. No, you guys were like the summer project ahead of them, right? Yeah. Almost 5 units. They just got to solutions today. No, I mean, the thing is that they don't do all the thermochemistry that you guys do. They don't do all of these concentrations. They basically, this unit for CP Chem is to learn molarity. And that's it. What's that? Yeah. Yep. All right. Which number did you say? Number 4? All right. So it says calculate the molecular weight of a compound if 4 grams of it plus 50 grams of water give a solution with a boiling point of 100.41. So we're looking for delta T of B equals, it says molecular weight. If it were an ionic compound, it would say formula weight instead of molecular weight. We always call it molar mass, which covers everything. But if you recall last semester, formula unit is like a molecule for an ionic compound. I think I told the story about me seeing the dog and saying, oh, what a cute Yorkshire Terrier. And then the lady was like, oh, it's a Yorkie poo. And I was like, whatever, nice dog, right? Because if you say dogs, then you cover everything. Same thing if we say molar mass, we cover everything. But this says molecular weight. So that tells us that the Van Hoff factor is 1. So we don't have to worry about it. So again, we want to find this molality. So we're going to take and divide both sides by the KB. So that is 0.41 divided by, what is it, 0.512? 0.41 divided by 0.512.
The answer is about 0.8007.
0.8008. That is the molality, that is moles per 1 kilogram. Well, we don't have 1 kilogram, we only have what? No. We only have
50 grams of water.
50 grams, right? So we will do the same math as before, 50 grams of water. Every 1,000 grams of water is 1 kilogram. Every 1 kilogram is 0.8008 moles of this solute. 50 divided by 1,000 times 0.0. 50 divided by 1,000 times 0.8008.
The answer is 0.04004.
0.4004. So that's how many moles I have, right? What is molar mass? It's
Grams.
grams per mole, right? It's the amount of grams that is equal to 1 mole. So we know the grams is 4. We know that this is the number of moles. So we take the mass and we divide it by the number of moles. That gives us the grams per mole. 4 divided by 0.04004. That's a fun number to say.
It's about 99.9.
We get 99.9 grams.
Will the sig figs on the test be pretty clear? Like how many to put it in?
In reality, with subtraction on this one, it should actually be rounded to 1.0 times 10 to the second. But with this test, I can't test you on significant digits on those math problems, if you remember.
Oh, so you're just gonna do like the rounding thing, like to like 1% or something?
Yep, 2%.
Okay.
What's the question, Emma? The molar mass is the mass divided by the number of moles, right? So from the molality here, from getting the molality, I could get the number of moles of this compound. I had 50 grams of water, and the molality that 50 grams of water had to be with this, right? So I used that molality to find the moles, which was this, the 0.4004. Is it 0.0? Yeah, 0.04004. That's the moles. Well, molar mass is what they want, molecular weight, the mass per mole. So if we have mass, grams, divided by moles, that's grams per mole. That by definition is molar mass. Yeah, this is the moles of just the solute. Because we had 50 grams of water, and in that 50 grams of water, 0.04004 were moles of solute were dissolved. And since 0.04004 moles of solute were dissolved, and that is equal to 4.00 grams of that same solute, by taking the grams that we have and dividing it by the moles that is equal to, we can find the molar mass. Right? If we have 2 moles of water, what is its mass? Time. Right? So what is that, 36? Right? So if we have 36 grams and we know we have 2 moles and that is equal to that 36 grams, if we take that 36 divided by that 2, that'll give us the molar mass. Does that make sense? Right? Yeah, that's the thing about this. I mean, we haven't had this much math intensity since thermodynamics, right? Isn't it kind of amazing? But isn't it kind of amazing how like now you're just assumed that you know how to use moles perfectly, right? Yeah. Are you gonna take AP Chem? Yeah. Who did? Oh, right. It's just the easiest AP course. I get it. Yeah. In AP chemistry, we expect you to be able to fix it. Like it's hard. I mean, it's probably. I would say that this is probably the most challenging science course because you guys are sophomores and it's like everything's brand new to you. But in the AP chemistry, I mean, some of the stuff we do, like tomorrow, they're making a buffer solution that resists changes in acid, adding an acid to it or adding a base to it. Like it's going to be amazing. Basically, you take, no, actually, it's our next unit. We'll see our next unit. Equilibrium. That's pretty cool. Your body does it all the time, right? Those of you that are runners, there's a buildup of acid in your what do they call that? Yeah. Lactic acid, right? What does your body do to combat that? Cramps? No. What do you do when you run? Breathe harder. You start breathing harder. So as that acid's building up, in your blood system, the body basically changes that to H2CO3, which we know H2CO3 breaks down into what? Remember that from our reactions last year? What could that break down into? Water and carbon dioxide. So what happens when you run? Well, yes, but your body makes this, and then it breaks down into water and carbon dioxide. So you start breathing out more carbon dioxide. Yep, and that's what allows your body's blood pH to not go lower than 7.3. No. So that we could what, like human faucets. The saliva isn't enough. This is gonna get interesting. I'm gonna go ahead and pause the recording, just so he doesn't say something no. Like a fountain? Oh my gosh, that's like, yeah, like, and they just have to stand there in the mall? What is going on? Like, this is like some weird stuff, like,
Like, if someone just spits water in my mouth, it's gonna be like, but then there's a water crisis.
all right, if there are no more questions, I'm gonna end it here, but I'm more than willing to take more questions if you have them. On who? Unwind now. UNWIND.
Are the answers to 15 and 22 posted online?
I don't know. Where is it? 15, let's check. Oh.
Have you ever seen 7 pounds? Have you seen 7 pounds?
This is what you guys are missing.
It's a really good movie.
15 through 22, it says.
Okay, thank you.
Yep. So yeah, real quick, was that Akshay?
Yeah.
So real quick, if you take a look, the format of these questions do not look the same. Like, it doesn't say the same thing at the top, but they are the same.
I think he gives away 7 of his orders.
Okay, thank you.
You're welcome. To tell you the truth, that's probably how most people learn chemistry, is by looking through problems that like this that other people have done. I mean, that's like the biggest way, I think. It's the way we learned it in college as well. All right, if nobody else has any questions out there, I'm gonna go ahead and stop the Zoom then and let you guys get out of here, because I don't want to waste any time that you guys have.
Mr. Jazz, I have a quick question.
Yeah, Brody.
How do you determine the Van Hoff factor for an ionic solution?
All right, let's do it. So do you remember last semester when we did a net ionic equation? Basically, we look at this as aqueous. So what does this break down into if it's aqueous? Well, we have a barium +2 ion, and we have 2 NO3 negative ions. What is the total number of ions there? 1 + 2 is 3. So the Van Hoff factor for this one is 3. If we had something like NaOH, Then you have one Na and you have one hydroxide. So the Van Hoff factor for this would be 2. Let's say we have C2H3O11. I'm sorry, C12H22O11. Then this is not a metal. So this is all one big particle. This will not dissociate. Even though it dissolves, it does not dissociate like an ionic compound. So the Van Hoff factor for this would be 1. What about this one? This is a tricky one. NH4 2SO4. That's ammonium sulfate. What's the Van Hoff factor for that one? What is the Van Hoff factor for ammonium sulfate? It's the name for the index, the I.
Is it 3?
It is 3. Sulfate is -2, so that's 1. Now the trick here is that a lot of people recognize nitrogen is not a metal, but ammonium is one of those weird polyatomic ions that's positive. So we have how many of the NH4s with that? 2. So for every 1 ammonium sulfate, you get 2 ammonium ions and 1 sulfate ion. Cool.
Well, we have to know like the hydration, like the hydration on like a metal ion with like the 6 hydrates and stuff. And use that to do like math calculations.
Are you talking about like aluminum dissolving and then it has 6 H2O on it?
Yeah, because I think we did that like a lab or something. I think the making the solution, we used the molar mass of like the whole like hydration
The
compound.
hydrates, yeah. If it has a hydrate, that is part of its molar mass, yeah.
So you would include that in the molar mass when you solve for like the molarity and stuff like that.
Yes.
Okay, thank you.
Yep, and that's got, yeah, that might be hard from not being at home and not actually doing that lab, like not actually physically doing it, but yeah, because that has that water absorbed in it, when you put that crystal onto the scale, it's weighing that water too. So you definitely have to include that in the molar mass of it. Otherwise, you don't have the true number of moles.
Okay, thank you.
Yep, I think Emma, you ran into that, didn't you? The molar mass of the cobalt 2 nitrate hexahydrate. That changed the molarity then. That's right, yeah. What machine? The Spec 20s?
Yeah.
I would say they were probably in the 70s, early 70s. I could be wrong. Yeah, they could be used to find impurities, toxicities, like poisons. Yeah. Mhm. All right, that's all I got. I'm gonna go and close it out unless somebody says something else.
Mr. Jackson,
Yeah,
did you get my email on Canvas about the lab?
I don't know. What did it say?
Basically, Canvas wouldn't let me turn it in. I
Okay,
don't know if the files are too big, but it wouldn't let me turn in either of the files.
yeah,
Or it might be my internet, but my internet has been working, and when I tried to try again, it just wouldn't load, or it would say submit failed.
okay. Do you want to give it a few days and then try it again? Because I probably won't
Okay.
get those until probably maybe Friday.
Okay.
Yeah, all right.
Yep.
And then we'll do it, we'll go from there. Maybe if we have to, you can email it to me, but I usually don't like that.
Okay.
Oh, wow,
Thank
yeah,
you.
I was in bed by that time.
Okay.
Yeah,
Thank you. Have a
just
good-
today at 9:30, yep. Cool. That's funny. Do you know Emma Gage? Yeah. She asked me what my favorite color was, and I think that I told her the color of the what we would call the electromagnetic spectrum that lithium gives off.
Yeah, we're going.
It's like this real scarlety red color. But what is my favorite element or compound? Chemical. I don't know.